Hello, everyone. Welcome back to Physical Geology 1403. Today is lecture 7. It is the last lecture of module 1. So we will have our full lecture and we will have lab time, and you are getting lab 4 today because this is the lecture we learn about lab 4. So even though you got another lab last time we met, you are getting this one today. There is going to be a little bit of overlap, and that's totally fine. You'll still have a week for both. All right. So on Thursday, 2 days from today, we will have our final exam review. Now, this is important. I'm going to remind y'all, I do not give you a list of things for the review. The review is dictated entirely by you and your questions. Okay? You come with questions, I answer them. Yeah.
And the exam just Thursday, right? It's this Thursday, right?
The exam opens the moment that I close the review. Okay, so the review ends, I open the exam. For those of you watching this online, I will post that exam review immediately. All of you have 24 hours to take the exam, with the exception of anyone who I've told you have an exception for. We have a firefighter in my online class. He is on shift for that 24 hours, so that's an example of when I would extend that deadline for an individual. However, the rest of you should be able to take it in that 24-hour period unless something really drastic comes up. Okay? There's no reason why you shouldn't be able to. If you work night shifts, take it during the day. If you work day shifts, take it during the night. If you're at school all day, take it in the evening when you get home. Right? There's some time during those 24 hours you can take it. Please come to class on Thursday with your questions prepared. That would be ideal. It's perfectly acceptable for you to go through your notes during that exam review process, but if no one comes with questions, it's going to be a pretty boring review. For those of you who are in my online class, please send me your questions no later than Wednesday evening. If you send them to me on Thursday morning, I probably will not see them before I walk in here to start our review. Okay? Please send them to me no later than Wednesday evening so I can address your questions for the review. Whether you're in my online class or my in-person class, your questions benefit each other. If you have a question about something, I can guarantee someone else in the class has that question too. Okay? You are not uniquely dumb, if that makes any of you feel better. Okay? We're all usually pretty dumb on the same level. And so if you have a question about something, please don't feel self-conscious about asking it. All right? All right, what else? I sent out a message yesterday letting you all know that I had to move the class movie night. We had it planned for February 23rd at 6 p.m. However, due to my wife's planning, I no longer am available that evening. So we are going to have it on March 1st, okay, at 6 p.m. in that room right there, 203. Because their projector is a lot more reliable than this one. It has a smaller screen, but it doesn't turn on and off all the time. And yeah, please come. We'll have a good time. It's going to be Dante's Peak, fun volcano movie. Friends, family, food, drinks, all the good stuff. What else? Oh, if you wouldn't mind sending some good luck thoughts my way. I am about to finish my application for a $40,000 fellowship for my PhD. And if I get it, it would basically pay for my entire PhD. So I'm really crossing my fingers that I get this. So positive vibes, please, that I can get that. Let's see. I think that's all I've got. So before we start on the new content, what questions do you all have for me? Anything at all from this module? Yeah. I can go into more detail on Thursday, but for now I'll just say your exam is going to be a mix of the usual suspects, right? Short answer, multiple choice, matching, ordering, true, false, those things, okay? Nothing real sneaky. There's no mineral or rock identification on this exam. Okay, that is preserved solely for the lab exam, which you'll get probably around week 6.
Because I was gonna ask, if there's gonna be like really hard questions like on like cleavage, for example, where if you identify cleavage on a rock.
Well, so this exam is over the things we talk about in lecture. This is a lecture exam, not a lab exam.
Okay.
We did talk about cleavage in lecture. I told you about the principle of cleavage.
Yeah.
The application of finding it, that's in lab. It is entirely possible that I ask you a question about what cleavage is. I will not, however, provide a sample for you to find it on.
Okay, good.
Not on this exam. You have a lab exam in week 6 where you will get 12 samples drawn from all 4 sample labs, and you will need to go through the whole identification process on that exam. But that's for a few weeks away. Let's focus on the exam you're getting in 2 days. Okay. Good questions. Anything else?
Can I make a Quizlet based on the last 7 lectures?
You can use whatever sources you want as long as you're only using your notes on the exam itself.
Also, my notes should be submitted by that time. It's been busy, but
Right.
I've got all my notes here. So.
Yeah, just make sure that you have your notes turned in. That would be ideal. So I can go through them and just double check and be like, okay, yes, they're following my rules, and it looks like they're generally keeping up with the course. Okay.
What if you have all your notes in just one doc?
On a what?
One doc.
On one document? You can submit screenshots for each submission. Good question. I'm gonna repeat all of this on Thursday, but remember, when you are taking the exam, literally close everything on your laptop, have nothing else running, just one internet page with your exam, and if your notes are digital, whatever program your notes are on, nothing else. Having anything else going in the background, you got Facebook on, you've got YouTube, you've got, I don't know, can you have Instagram on a laptop? I don't know. You have any of that stuff going, you run the risk of your computer, its internet capabilities may get overloaded. It happens a lot if you have a lot of things going, and it will often refresh the internet connection to try and clear up some space, to try and get a stronger connection. And if that happens, Blackboard automatically submits your exam. So just don't play yourself, okay? Just the exam, and if your notes are digital, your notes, okay? Keep it as easy as possible. All right? Other questions? I'll have a lot more to talk about on this subject on Thursday. And again, please come with your questions, and online students, send them to me on Wednesday, no later than Wednesday. Okay, well then let's jump into today's lecture, all right? We ended last time with a conversation about sedimentary rocks. Today we're learning about the third and final type of rock, metamorphic rocks, okay? So let's start off with looking at this picture. Tell me what you see here.
A log, like, it looks almost as if the rock side is like almost like contorted or like compressed almost.
All right,
Like
so
almost layered.
okay, so you see layers, right? But what's weird with these layers? What was the word you just said? Contorted?
Yeah.
What are other words we can use to describe what's happening to these layers here?
Like press against one another.
Can you all see these, by the way?
Yeah.
These aren't doing what layers typically do. What do layers typically do? Yeah, they just stack flat on top of each other. What are these doing?
They kind of overlap and make a curve on each other.
They're curving. What else?
They look weathered.
Well, okay, so they're on the surface. Yes, there is definitely obviously some weathering going on here. It's next to the seaside right there. There's a lot of weathering going on this cliff from wave action and stuff. That's true. There's a lot of weathering. But the rocks themselves, we see that those layers are curved.
Possible erosion from wind.
Well, there's definitely that happening, but talking about the nature of, yes,
They're just layered in multiple directions.
they're layered in one direction.
Multiple directions.
Oh, in multiple directions. Oh, I see what you're saying. Okay, so what we're actually looking at here is we're looking at this from a couple of different angles, okay? So we're looking at it at this angle, and then you may not be able to tell in this picture, but it's actually curving over this way, which is why you can kind of see this shape but it appears to be coming from a couple different directions. Okay. Other words we can use to describe this.
They all kind of just look smushed together, honestly.
Smushed? Well,
They're pressed.
yeah. What would happen to cause layers of rock that were flat to curve over like that? What needs to happen? Yeah. Pressure. That's doing this, right? Yeah, they've been smushed. They've been curved. They've been folded. And that's the term we're looking for here. These rocks have been folded, and folding is characteristic in metamorphic rocks. You can find it in sedimentary rocks, but it is very common in metamorphic rocks, and we'll talk about that today. Okay, so what is metamorphism? Metamorphism is what we call a change that occurs within a solid without it changing its state. Okay, it does not become a liquid during this process. It does, however, change a lot of its characteristics. You can see a change in the texture, the minerals, and the overall chemistry of your rock through metamorphism. Now, metamorphism is a process that is kind of occurs on a graded scale, okay? So you can have very lightly, subtly, barely even noticeably metamorphosed rock. And you can have rock that has been so metamorphosed that you can't even tell what it originally was, okay? And there are variations between those two extremes, okay? So what is it that causes rocks to become metamorphosed at all? There are a couple of factors at play here. The first one being heat. Someone remind me what heat is.
It's particles moving very fast. It's energy. Yeah. Well, heat is the presence of energy. Usually, moving very fast or vibrating.
Heat is a form of energy.
Yeah.
Okay. And that energy is causing our molecules to do what?
Shake around and those bonds can break.
Vibrate extremely fast. Now, as you increase the heat of an object, eventually it will reach a threshold where they are moving so fast that they cannot maintain their bonds. They disassociate from each other, they break apart, and your material melts. However, there is a threshold for that. What happens if I add energy, but I don't quite reach that threshold? What do my atoms do? They still have their bonds, but they have so much energy, bless you, that they become what we call mobile. They are more willing, I guess you could say, to break off and reform with something else. Now, this doesn't happen all at once, so our material doesn't melt. And it's situational. So it won't just do it because of whatever. It'll do it because there's an easier bond next to it. Okay, something that is more stable at that high temperature. Okay. Remember, we're changing an environmental parameter here. We are increasing the heat of an object. We have, therefore, changed the environment around that object, and therefore it is not stable. Remember, in general, objects in nature, all things in nature seek a state of stability. Well, our material, a rock in this instant, is going to change metamorphically to become stable in that new environment. Okay, bless you. So this will happen often through recrystallization. If you start with a rock that contains a lot of fine-grained minerals, let's say I've got a shale, for example, okay? Shale, clay and silt-sized particles, right? We learned about that last week. Microscopic in size. Well, if I increase the heat to metamorphic conditions on that shale, it's not going to melt, but those individual clay and silt-sized particles, being less stable at that temperature, are going to recrystallize together and make larger crystals. They actually make mica as a result of metamorphism. Clays will often recrystallize into larger mica crystals. And you can end up with a rock that looks like that. This is a type of rock called schist. Okay, we'll talk more about that today. schist often is the result of metamorphosed shales and mudstones because the clays metamorphosed into micas, which you can see in there, right? Why did they do that? Because mica is more, say it louder, stable in those conditions. The clays were not, the mica is, and therefore they recrystallize into that. Now, obviously, you can't recrystallize into something you don't have the ingredients for. Clays aren't going to recrystallize into diamond, right? That's called alchemy, and that's not actually, that doesn't exist, okay? We can't turn lead into gold. You can't make something out of nothing that was there before, okay? This is chemistry. Excuse me, chemistry. You remember that example of a chocolate chip cookie I gave you when I was explaining the difference between a mineral and a rock? If I have all the ingredients for a chocolate chip cookie, and they're just here on my countertop, can I make an oatmeal raisin cookie out of them? No, I don't have oatmeal or raisins in a typical chocolate chip cookie, right? You can't make something out of ingredients that weren't there before. And so, because clays contain all the ingredients to make micas, that's what's made, and it's stable. Okay? By the way, I just need to back up here a minute. I know talking about cookies right now is probably a mistake, but we all had that traumatic experience where we bit into an oatmeal raisin cookie as a kid thinking it was a chocolate chip cookie, right? And that scarred us. It's time to stop lying to ourselves and admit that oatmeal raisin cookies are actually bomb. Okay? No, they are awesome, and y'all know it, and you need to admit it. All right? Yeah, oatmeal raisin cookies are so good. Okay, yes, warm any cookie is so good. Okay. All right. Okay. Where does this heat come from? Y'all remember our geothermal gradient? Someone remind me what the geothermal gradient is. What was the definition I gave?
It was a point, what's the word? Okay, so you need heat to melt a rock, right? But you add more pressure and the rock doesn't want to melt. So you need either more heat or less pressure to make it melt.
It is a balance between heat and pressure. That is true. But the definition of the geothermal gradient that I gave was, does anyone remember? Don't need it word for word. I just, I need to know that you guys know the gist of it. I'll give you a little bit. The rate at which heat increases the deeper you go underground. That's the definition I gave. That's a very basic definition of the geothermal gradient. Okay? That's not one of the things you need to know word for word. I just need to know that you understand it in concept. It is the rate at which heat increases the deeper you go underground. And why does it do that? You're getting closer to the core, which has a lot of heat. Radioactive heat in particular. There's a lot of radioactive isotopes that are giving off radiation and heating everything up around them, right? It is cooling off over time, but it's going to be billions of years before it totally cools off and we go all Mars shaped, right? So the geothermal gradient is a thing. It gets hotter the deeper you go underground. Up until about 500 kilometers, which is deep enough that we don't really care about it in this context, okay? We're just going to say that the average heat increase for the geothermal gradient, at least as it pertains to the crust, is about 25 degrees Celsius per kilometer of depth. The heat is increasing by 25 degrees Celsius per kilometer of depth. That gets hot fast. Do you guys remember I told you about diagenesis last time we met? Do you remember what the temperature range for diagenesis was? Go back through your notes. Hopefully, at least some of you wrote this down. I gave you a range of temperature during which diagenesis takes place. Huh? 152 to 200. And remember, diagenesis is any change that occurs to that sediment after deposition, but before what change in particular? Lithification happens during diagenesis. Diagenesis is any change that happens to the sediment after deposition but before metamorphism. Bingo. So if diagenesis ends at 200 degrees Celsius, that must be where what starts? Metamorphism. Okay, metamorphism starts at about 200 degrees Celsius. The geothermal gradient increases at 25 degrees Celsius per kilometer of depth. How deep do we need to be before metamorphism typically begins? No, at 200 degrees Celsius, at 25 degrees Celsius per kilometer, how many kilometers down do we need to be? 8 kilometers. 8 times 25 is 200. 200 divided by 25 is 8, right? At 8 kilometers, you have enough heat to start metamorphism. Now, there are some things that can cause metamorphism to happen before that. Plate interactions, right? Subduction of one plate under another. The collision of two tectonic plates that are of equal mass and therefore do not subduct. They make a massive mountain range, right? These forces can create heat at higher depths than 8 kilometers. Okay? 8 kilometers is how deep you would need to be if this was a simple burial situation. Let's say out here, I've got a whole bunch of sediment collecting out here in this inland basin, and it's just piling on top of itself, piling on top of itself, piling on top of itself, until finally what was once on the surface, what was deposited on the surface, has been buried 8 kilometers deep. At that point, the geothermal gradient causes it to metamorphose. Okay? You can get metamorphism occurring at these boundaries between plates. You can get metamorphism occurring down here in a mountain range. You can get metamorphism occurring around a magma chamber because it's hotter than 200 degrees Celsius, right? We'll talk about that today. All right, some other things that can influence metamorphism because of heat. Fluids, mostly water. If I have water in a rock as it's metamorphosed, I may get a totally different type of rock than if I had no water before. Okay, the presence of those hydrogens and oxygens and the fact of what water does chemically could create a totally different type of rock. So that's what we call a hydrous rock. Okay, if it's got water in it, making it chemically active, okay, chemically active water during this process, it'll make some form of hydrous metamorphic rock. Water has something to do in the composition. An anhydrous one that has no water during the process, you can end up with a totally different type of rock. Okay, the presence of fluids in this process, we call that metasomatism. Okay, so metasomatism will make a metamorphic rock thanks to the presence of water during the process. Okay. The presence or absence of water. Bear that in mind. Okay. Then there's the influence of the rock you had in the first place. Just like you can't, like I used that example before, you can't make an oatmeal raisin cookie out of chocolate chip cookie ingredients. Well, that's what I'm talking about here. Your parent rock is the original rock. Okay. That's the mix of ingredients you had to work with in the first place. Now, you can introduce new ingredients to the equation. How do you suppose that could happen? Okay, so you can get other rocks involved, or you can get new materials brought by something. Huh?
Magma flows?
Not a magma flow. Something else flow. Water.
Rain.
Water, remember, contains a lot of dissolved minerals. We talked about that last time. What happens if I have rock that is undergoing some form of metamorphic process, and then water-rich in dissolved minerals comes into the equation? Not only do I have water messing with it, I've also got all the minerals that water was carrying. So maybe now I can make an oatmeal raisin cookie, right? I make a different rock out of materials that weren't present in the original rock because the water brought new stuff. Okay? Now, besides heat, the other major factor that contributes to metamorphism is pressure. There are two types of pressure, okay? Confining pressure and differential stress. Confining pressure. To understand this, I want you all to close your eyes. All right, everyone close your eyes. Just take a minute, take a few breaths. Do you feel the pressure of the air on your body, on every surface of your body? Can you feel that? If you can, I'd be amazed. Guess what? We're used to it.
Yeah.
The moment you were born, it may have been a little uncomfortable because the pressure in your mother's womb was slightly different than it is in the atmosphere. But ever since then, you got used to it, so we can't feel it. And yet it is there. We are experiencing equal pressure on every surface of our body because of the atmosphere that we reside in. Now close your eyes and imagine you're at the bottom of a 12-foot pool. Can you feel that pressure on every surface of your body? Yeah.
I can feel it in my ears as well.
Yeah. Every surface of you is feeling that pressure equally. That's because you are experiencing equal pressure on all surfaces of your body that you are not used to. Okay? That is confining pressure. Equal surfaces on all from all directions on any given point. Okay? If I picked 1.1 square centimeter of rock a kilometer underground, that square centimeter of rock is experiencing pressure from all directions equally. That is confining pressure. Okay, so that causes that squeezing effect, but it won't cause any deformation. However, the other kind of pressure, differential stress, that's another story. I need a volunteer to come up here with me. Bless you. Oh, over here. Go and take that end of these. The end. Yeah. So move over here. Let's try and line these up so they're a little easier to see there. There we go. Okay. Okay. Got them? Okay, pull the top. Pull it. Pull it top. Tight, so it's tight. There we go.
Got you.
Okay. You see these three layers of rock? Red, green, blue, different from each other, right? Pull it a little tighter. There we go. Flat, horizontal, just like they were originally deposited. Differential stress is when rocks or other materials experience unequal stress. Say, for example, on the plane we're looking at, from the left and right, on the horizontal plane. What happens if I push these layers of rock towards him? What'd they do? They folded. Ooh, that's a word we've heard today already. Where did we hear that word? Yeah, describing that picture on the very first slide. And what were those rocks doing? They were bent over. They were curved. They were folded, just like these ones are. That's what caused it. Differential stress. Thank you. Differential stress is going to cause deformation because those layers of rock are experiencing unequal stress. Same way this sheet did in my example I gave earlier. Okay? Camera. There we go. All right. Just like the sheet of paper does when I push stress on it from these directions. Excuse me. Now, notice the direction of deformation. If I give stress on this sheet of paper or on those layers of foam on this plane, horizontal to yours and my perspective, what direction does the material deform in? Up or down, or both. You can see this. So this is important. Differential stress will always cause deformation perpendicular to the direction of stress applied. In the same way that if I had a ball of Play-Doh in my hand and I pressed on it this way, how does it reshape itself? Up and down and out. Any direction it can, perpendicular to the direction I am pushing on it. Same principle here. Okay? So differential stress causes deformation perpendicular to the direction of stress applied. Any question about that? No? Well, then let me show you this. Look at these grains of minerals in this rock. What do you notice about them? They're squished. Look, they're all generally squished along the same plane. How do you suppose that happened? What kind of pressure?
Confining.
Confining is equal in all directions. If it got squished along a certain plane, that means it must have been differential stress. Now, this introduces a new subject called foliation, which I will get to on the next slide. But for now, let's just say these have obviously been squished by differential stress. From what direction? In this case, the stress came from up and down. Why? Because they deformed laterally, according to our perspective looking at them. This is very valuable. I can look at a metamorphic rock that has been flattened, where the minerals have been flattened like this, and I can tell what direction the stress that caused it came from. And that can do things like allow me to interpret ancient mountain building events. Okay? Why? Because mountain building events are largely responsible for a lot of this differential stress. Plate collisions and such. Okay? Just another clue that we can get for interpreting Earth history. Now let's look at a few more complicated examples. See if you can piece these together. Take a look at these layers. Oh man, doesn't that look fun? What are we looking at here? My layers are doing that. What is it?
It looks like it's on all spikes, though. Okay, it would be.
It's okay. Shoot your shot. Tell me what you think. What are we looking at?
It's confining us with pressure. Because it looks like it's on all sides, kind of. So.
What do you guys think? Is this confining pressure or differential stress? Why is it differential stress? It's deformed. You can't get deformation with confining pressure. You wouldn't have anything with confining pressure. So we're looking at differential stress, but what has happened here? What's changed directions? You got it. Okay. What we have here are probably 1, 2, 3, maybe another 2 different events that caused this folding effect from those directions, and then another even larger one that caused these previously folded layers. So we've got layers that did this before, and then a larger event caused those to form a larger fold. Like that. We're looking at several differential stress situations here, one after the other, possibly 3, depending on how we want to interpret those smaller ones and what happened before that big one. But we can look at a very, very folded metamorphic rock and interpret things like there were multiple differential stress causing situations here. And then we can figure out what they were using other clues. Okay, excellent. Well observed. I just want to say most people don't pick up on that. I usually have to say it. So well done. Okay, so now we've got a few other things. Here we have some layers of shale, and you can clearly see the bedding planes for these 4 distinct layers of shale. 1, 2, 3, 4. You can see the flat bedding planes. However, this is not breaking along those bedding planes. Do you notice the angles that it's breaking at? Yeah, it's breaking along planes like that. Why is this shale, which should be breaking along planes parallel to its bedding, why is it now breaking at an angle perpendicular to its bedding? Because what? It's not confining. Remember, the reason why shales break along planes of its bedding is because clays are flat. They lay flat on each other in a shale. And so they break along those very thin layers. Why are all of a sudden those thin layers not parallel to the bedding plane that they were deposited on? What? I feel like you're close to the answer. Let's see. Try and explain it. Is the rock at an angle? Or are the clays at an angle? The clays were originally deposited parallel to the bedding. Huh? Not because of gravity.
Pressure forced them sideways?
Ah, what pressure?
The
Differential stress causes them to reorient at a different angle. And now we've got them breaking. This rock is breaking at this angle. When I look at this, how can I interpret the direction the stress came from? The differential stress is always going to be blank to the direction perpendicular. My stress came perpendicular to the direction that all of those minerals have been realigned to. Okay? So if I think of this as originally horizontal, I can tell at what angles the stress was applied. It's pretty cool, I think. Right? Any questions about confining pressure or differential stress?
It would cause something, because we need pressure to do that sort of thing, but it's above the ground. So what kind of thing would cause that to come to the surface?
Tectonics or simple weathering, right? So this is all happening deep underground, obviously, because you need the heat and pressure to let it happen. So what causes these metamorphic rocks to come to the surface? Excellent. Well, let's say that I've got metamorphic rock deep underground, and the tectonic situation causes a mountain range to be formed. Let's say two plates collide with each other. Well, all of a sudden, a lot of rock that was underground is going to be pushed up to the surface. Let's also say this rock is deep underground, but millions and millions and millions and millions and millions and millions and millions of years of weathering and erosion happen. It's going to eventually come up, right? It's going to get pushed up to the surface. It's going to be exposed.
It does look like a weathered surface.
Yeah, very weathered, right? Question, what else? Is this all making sense? Okay. All right, well then let's move on to foliation, like I promised we were going to get to. Foliation is a metamorphic texture. You'll learn about igneous textures, right? Foliation is really kind of the only metamorphic texture we discuss. Non-foliated and foliated rocks is the broadest definition of a way that you can break metamorphic rocks from each other, how you can differentiate them from each other, okay? And there are different degrees of foliation. Remember, foliation is a parallel alignment of minerals thanks to differential stress. Those clays that were flat in one direction were reoriented in another direction, perpendicular to the direction of stress applied. And that's a foliated rock. Okay? So there are different degrees of foliation, usually corresponding to the degree of metamorphism that took place. So a very slightly metamorphosed rock will usually also have slight foliation. And that's what we would call a slaty foliation. In some of the literature, I just want to caution you, like if you look up additional information online, you may see some people refer to that as rock cleavage. We don't call it that in my class because we already learned about mineral cleavage and that would just confuse you. So this is all foliation as far as we're concerned, okay? Slaty foliation, very light foliation, light metamorphism. Schistose or schistosity, okay? That's kind of a confusing word. I would say that a rock has schistosity to describe it as being moderately metamorphosed or foliated. And I would describe it as schistose, right? So it just depends on the situation and which word you would use. Gneissic means a high degree of foliation and usually corresponds to a high degree of metamorphism, okay? And then there's non-foliated rocks. What kind of pressure do you suppose makes non-foliated metamorphic rocks? Confining pressure. Bingo. Confining pressure does not cause deformation and therefore will not cause foliation. Okay. And then there is porphyroblastic texture. Porphyroblastic is essentially the same thing as porphyritic was in igneous rocks. Someone remind me what porphyritic igneous texture was? You remember? I was looking at Shanice. She looked up like, oh.
Didn't have other stuff in it? Kind of?
Be more specific. Large crystals surrounded by microscopic crystals. Remember, you've got your large crystal rocks, which are phaneritic, cooled slowly underground. Your small crystal rocks, aphanitic, cooled quickly above ground. When you have both large and small crystals in there, large, easily seen, and microscopic, that means that you had some partial cooling or partial melting and then rapid cooling, okay? That's porphyritic. In metamorphic rocks, we call it porphyroblastic. And that is when you have a very large, easily seen crystal surrounded by much smaller crystals. So it looks very similar to a porphyritic igneous rock, but this is obviously, look at that foliation. And this is mica. This is pretty much all mica, this other stuff in there. This is obviously a metamorphic rock, but it has a large crystal in there, and so we're calling that a porphyroblastic texture. By the way, can anyone tell me what this mineral is, just by looking at it? Anyone want to take a guess? Huh? The mineral? What that is?
I remember it was a very dark red hard one. It's hard.
Yeah. Garnet, good. We got some geologists in here. Okay, that is a large, beautiful garnet in what is actually a foliated schist right there. Okay, that rock is schist, and it has a porphyroblastic texture because it contains a garnet. It's also foliated, so you could call it foliated and porphyroblastic. However, porphyroblastic textures can also be true in non-foliated rocks. So you just kind of got to describe it. And this is actually what you'll find when we learn about metamorphic rocks. The way that we name them is based entirely off of what they got in them. So I would call that a porphyroblastic foliated mica schist with garnet. Literally, that would be its name. There are so many varieties of especially schist that we don't really give them a name, like granite or diorite or rhyolite, because there are so many varieties, okay? So it's just a blank, 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 blank schist based off of whatever it's got, okay? All right, so foliation can come about in a couple of different ways. First of all, you can get a rotation of minerals. So like those clays I talked about earlier, already flat. All they do is rotate, reorient themselves based upon where the stress is coming from. That's where that initial foliation comes from, like in that picture of the breaking perpendicular to cleavage planes or to bedding planes came from. Okay. Then you can get recrystallization. Recrystallization will often happen when you have a slightly higher degree of metamorphism that causes your mineral crystals to start changing with each other and reshaping to be perpendicular to the direction of stress. Very simple example of that. Here you go. And remember this? Diorite. And this is schist. Or sorry, gneiss. This is gneiss. I mean, it is a gneiss rock, but the name is also gneiss. G-N-E-I-S-S. Okay? Gneiss. Do you see how they contain the same minerals? What's happened here? They recrystallized to be perpendicular to the direction of stress. Isn't that cool? Same minerals at play, both are chocolate chip cookies, right? It's just one chocolate chip cookie reoriented all of the ingredients, right? And then we can get flattening. Do I have? Don't. Let me grab it from over here on the shelf. Could have sworn I had one out here. We've got flattening. Okay, so large rounded crystals or grains will get squished flat perpendicular to the direction of stress applied, right? Like you can see here. This looks like it was probably a conglomerate before it got metamorphosed, right? Judging by the size of those grains in there. Pass this one around that direction. So these are three ways you can end up with foliation in a metamorphic rock: reorientation, recrystallization, and flattening. Now let's talk about the different degrees of foliation. Slaty foliation is when you have very thin, flat layers because your stacked minerals have reoriented perpendicular to that direction of stress. Okay, so this is typically found in slate. Remember I told you metamorphic rocks names aren't that original. You'll often find slaty foliation in slate. Perhaps you've heard of slate. It's commonly used for building material, flooring, roofing, sometimes walls. Okay, you can crack it because of its foliation. You can break it into very flat plates like this. This is slaty foliation. This is low-grade metamorphism. The next step is moderate metamorphism, which is often accompanied with schistose foliation. Our flat planes from our slate, remember, this is all a degree, right? So if I take my shale and I slightly metamorphose it, I'm going to get a slate. If I take that slate and I metamorphose it even more, I'll get a schist. Now those flat foliation planes are starting to undulate slightly. You can kind of see they've got this wavy sort of, when you look at it edge on, you can see it's kind of got that wavy sort of edge, not perfectly flat anymore. Okay, and what's happened to our grain size? We now have large micas, easily seen. There's even a few garnets in there. Okay, this is moderate metamorphism. Then we've got gneissic foliation, which is the highest degree of metamorphism and the highest degree. Oh, I already passed the gneiss around. Okay. It's the highest degree of metamorphism and the highest degree of foliation. Where's the gneiss at right now? Right there. Okay. When you hold the gneiss up, what do you see? Do you see layers? Yeah, Shanice has the gneiss right there. So it's okay. When you look at it, do you see a continuous layer in each of those minerals? Or do they kind of start somewhere and then go and then end somewhere? Follow one of those black minerals. Does it continue as one distinct layer for the whole rock? No. Gneissic foliation is different from the rest because it is not layer-like. It's more banded, okay? Because what's happened in this situation is your minerals have reoriented perpendicular to the stress, and then because of the incredible amount of stress involved here, they've kind of been smeared, okay? Like squished, flattened, smeared through the rock, okay? And that's very characteristic of gneiss. It doesn't really have layers so much as it has smeared minerals, or banded minerals, we call it, okay? Are you seeing if the schist is magnetic?
Yeah, I was curious because it was kind of.
Okay. All right. Now let's talk about some non-foliated textures, okay? So non-foliated rocks don't have any deformation. There's no foliation. If you see foliation, you're not looking at a non-foliated rock. That should be obvious. Sometimes it's obvious and people don't catch it. But it's non-foliated if it's the result of confining pressure. Okay? So a non-foliated rock will not have those layers. It may have porphyroblasts, but it will be made out of generally large crystals, okay? There are a few exceptions. I'll talk about common non-foliated rocks here in a little bit. And then porphyroblastic, I obviously already talked about, large crystals in a matrix of smaller crystals, like that one I passed around earlier, okay? And those porphyroblasts are typically garnet, starlite, which you saw in lab 1, or andalusite, which is not one that I've included in our class, okay? But those are the 3 most common gems or minerals that you can find in porphyroblastic metamorphic rock. All right, so how do you go about identifying a metamorphic rock? Well, you've learned about textures, non-foliated, foliated, and porphyroblastic, right? Obviously, grain size is going to be a factor. Why? Because, well, the degree of metamorphism will help you figure out, or the grain size will help you figure out in general the degree of metamorphism, okay? As more metamorphism goes on, you end up getting larger grains most of the time, okay? Larger crystal sizes. The composition is key in pretty much all of these identification exercises, right? Same way that you found the minerals in igneous rocks and in sedimentary rocks, you now know how to find the minerals in metamorphic rocks. You know the tests, you know how to identify them, you've got those resources, you got that know-how. If you can, figure it out, right? And yeah, metamorphic rocks are going to be made out of multiple minerals, just like igneous and sedimentary rocks were, okay? And then through just knowing those things, you should be able to come up with a rock name, texture, grain size, and eventually, potentially, you may even be able to figure out what the original parent rock was just by looking at the composition and how metamorphosed it is. That's something we can figure out. You're not required to for the lab. I'm just saying that you probably would be able to, okay? So some very common metamorphic rocks. Slate, I already passed the slate around, the big, wide, flat one, okay? Often used as building material, okay? This is low-grade metamorphism, foliated. Thank you, just leave it there, okay? Just like how shale changes its color, or doesn't change its color, but has a certain color based upon what its parent rock was, or what it's made out of, okay? Slate is the same way. So if I have a red shale, I'll probably have a red slate. If I have a green shale, I'll probably have a green slate, so on and so forth. Phyllite. Let me pass around some phyllite. Phyllite represents an intermediate phase, a between phase between slate and schist. Remember, slate is low grade, schist is medium grade, phyllite is between the two. As I pass this around, you'll be able to notice how its flat foliated layers are slowly, like they've started to develop that slight curve to them. And you're going to notice it's a little bit glossy when you shine it in the light. That's because our clays have begun the process of changing into micas. This is our in-between, between slate and schist. Okay? Then there's schist, which I already passed around. That schist is medium grade metamorphism, often has large grain sizes, usually micas. Because there is such a wide variety of schists, depending upon so many different characteristics, so many different factors, we actually differentiate them from each other based upon what they are made out of, right? And so, like I said earlier, that one I passed around, I would call that a muscovite mica garnet schist. Why? Because it's made out of that silvery mica, which we know as muscovite mica, and it has those tiny garnets in it. Okay? There are a lot of different varieties, but we differentiate them based upon what they contain. And then we've got high-grade metamorphism, which is nice. Okay, so it's got that banded appearance. Usually some combination of feldspar and amphibole. Okay, that's usually what those banded minerals are. Okay, so in the case of the one I passed around, sodium feldspar, hornblende amphibole. Okay, they can contain quartz. Okay. They are extremely hard, and this is another one of those minerals, or excuse me, another one of those rocks that is often marketed as granite. And you can see why, right? The colors look about right. And yes, it does contain quartz some of the time. Not all gneisses have quartz. These minerals, well, tightly packed together, making the rock as a whole hard. The minerals themselves are not that hard. And yeah. Can they have vesicles? Not really. Yeah, I don't think I've ever seen a metamorphic rock that had vesicles or holes that weren't formed after the rock formed anyway. Yep. These minerals are still as the same hardness as they are in an igneous rock. And so when you market this as granite, you may not get what you think you're getting. Okay? And they have varying compositions. Some have more amphibole, some have more feldspar. What's the best way to tell if you're looking at a gneiss or a granite? No, gneiss may have some quartz in it.
In a large crystal.
They both have large crystals, easy to see, but what's the difference between the crystals? The foliation. Granite's not going to be foliated, right? Granite has randomly oriented minerals that grew wherever they grew from the magma. Gneiss is foliated, and that's your best way to tell. So if you walk into your countertop store and they're like, we got this brand new shipment of granite in, you're looking at it, it's like, excuse me, that's foliated. That's not granite. And their jaw drops because they realize they ain't dealing with an idiot, or they have no idea what you're talking about. Okay. But yeah, there you go. Okay. Non-foliated metamorphic rocks. Marble. Y'all have heard of marble before, right? Marble. Marble is a metamorphic rock. Marble is the result of metamorphosed limestone or dolostone. Okay. It's made out of calcite, which means that if it's from limestone is going to react to what? HCl, hydrochloric acid. It will bubble. If you think you're looking at a marble, you can test it with hydrochloric acid. That's a quick, easy test to see if it's marble. Also, that is effervescence. Okay? It is as hard as calcite. It's a 3 on the most hardness scale. It will not scratch glass. This is another material that is often marketed for building or for countertops. Don't do it. You can drop a butter knife on this and it'll scratch it. Okay? All right. The coloration that marble has, there are lots of different colors of marble. The most spectacular one I think I've ever seen was a Picasso marble, which I should have a sample of somewhere in my office, I believe. It's got browns and yellows and blues. It's beautiful. But the coloration comes from whatever sediment was in the limestone before. Remember that not all types of sedimentary rock are exactly distinct from each other. I can have a sandstone and it has 5% clay in it. I still call it a sandstone, right? I can have a limestone and it might have 10% clay in it. I still call it a limestone, but that clay that's in there when that limestone gets metamorphosed is going to color the limestone based upon whatever it is. It could be an iron-rich clay, it could be a chlorite-rich clay. Whatever the case, your limestone is going to get colored by those impurities. That's where the color comes from, okay, during that metamorphism process. Quartzite. Actually, here, let me pass some of these things around. I've been going through them. Here's the marble. Where's my quartzite? There it is. Okay, here's the marble. If you don't believe it's marble, you can drop some acid on it. Is that a joke about dropping acid? Okay. It is, yes. Okay, this is quartzite. Quartzite is non-foliated, metamorphosed sandstone. It's got that high quartz content, and so those quartz grains are going to fuse together and make an even more compact rock. This has all the same properties as quartz. It is just as hard, right? So I know this is quartzite because of all of the fused sand grains, but also oftentimes you can see some of the structures that were in there before. Most structures get destroyed, but some of them, like bedding planes, there's a bedding plane right here. This chunk of quartz I'm looking at. Sometimes that can be preserved. Do you see that? That bedding plane right there? Yeah, look at that. It's pretty cool. Okay, quartzite, metamorphosed sandstone. Very hard. That, oftentimes, they will mark it as just quartz. They will say, you want a quartz countertop? We got you. I don't really nitpick that because it's technically true. But if they call it granite, it's a problem. Okay? Can you all tell how many arguments I've had with countertop salesmen? I'm not going to say it's a hobby, but it's fun. My countertop is granite. You better believe it's granite. I know it's granite.
You replace countertop yearly just so you can have your.
No. So we built our house. I came here from the pipeline in Montana, so I had some money, and then we paid for them to build us a house, and I had none. I still have none. But because we got to choose how our house was built, I got to pick all the things, the cupboards, the countertops, and all that. And so they put a selection in front of us of 7 or 8 different options we could have for countertops. I'm like, no, maybe. No. That's the one, right? When you know, you know, and then you can use it. Okay. Any questions about these different types of metamorphic rocks? Okay. Let's talk about the environments in which metamorphism can occur. Contact metamorphism is what we call it when a rising magma body, make sure you're putting that glass on the table. I don't want you to accidentally cut yourself if it breaks. Okay. Is when a rising magma body heats up the rock around it. Now, obviously, it's going to melt the rock immediately in contact with it, right? It's gonna melt everything it's touching, but the heat is radiating through the rock around it. Okay, so what do we got here? Prior to the invasion of this magma chamber, we had shale, limestone, quartz sandstone, and shale. What is my shale going to metamorphose into? Huh? Oh, you're reading the slide, are you? I haven't talked about this yet. I was hoping to catch some of you. I thought you'd say slate. Glad you didn't. That's a good sign. Okay. When shale or other mudstones are metamorphosed in confining pressure, not differential stress, because remember, differential stress is going to make slate. When you use confining pressure to metamorphose shale and other mudstones, you get hornfells, which looks like this. It's basically a baked mudstone. It's a brick. It's basically a brick. Okay? Same clays. Nothing's really changed there. It's just gotten baked and cooked real hard. Okay? So that is going to make hornfells. The limestone is going to metamorphose into, say it louder, marble. The quartz sandstone, quartzite, and the hornfells, or the shale into hornfells, right? So I'm going to get layers, this sort of halo of metamorphic rock around my magma chamber. We call this an areole, okay? That's that word right there. Zone of metamorphic altered rock around a magma chamber. And this is actually a real one in real life. This is a mountain in New Zealand. You can see the igneous pluton, okay? That's made out of diorite, okay? That's why it's so pale in color. That is an igneous pluton, and this is a hornfells areole, okay? Also called a roof pendant because it's just hanging out on top. But you can see the sharp contrast there between what was igneous rock and what is metamorphic rock. The heat from that magma causing the metamorphic rock. This is confining pressure. There's not going to be any differential stress here. That magma chamber is not creating a massive amount of stress pushing out to the side. It's melting its way up. So we still have just the confining pressure of the depth at play. Okay? Then we've got hydrothermal metamorphism. So we're at the bottom of the ocean. There's a divergent plate boundary. Two plates separating away from each other. Remember how that looks? We've got our looks kind of like that. And then right here, that's where our magma is because of the lower pressure zone. Magma is coming up to the surface, making new rock, getting pushed to the side by new rising magma beneath it. And that's what's adding on to the sides of both our tectonic plates here. Well, because this is constantly getting pushed and shoved to the side, we're going to get cracks in these plates. Do you know what we call those cracks? We go over this in a later lecture in detail. Those are called faults. A fault forms, okay? These cracks allow water from the ocean, okay? Here's our ocean surface. Allows water to kind of seep down into these cracks, into the crust where it's really hot. That water is going to dissolve metals out of that really hot, chemically active rock. That's going to make different types of metamorphic rock. The result of that is going to be things like talc schists and serpentinites, different types of metamorphic rock formed down here in the crust. And where do those metals go? The metals are dissolved in that water, which is now extremely hot. Thanks to convection, it's going to rise up and it's going to come out of the bottom of the ocean, out of the crust at the bottom of the ocean near these tectonic plate boundaries. We call these black smokers. If you've ever watched any kind of Discovery Channel or National Geographic special about the bottom of the ocean, they will always talk about these. Okay? This is what it looks like. What does that look like to you?
Yeah. Or like raw sediment.
It looks like smoke. What?
I was gonna say that like it's also it's a high entry form for deep sea organisms as well. That's like second feed off of the air.
Something that we talked about in 1404 is it is widely believed that life began around these black smokers at the bottom of the ocean. Why? Because that isn't smoke. Those are that dissolved metal that was in the water. Okay? Super hot, boiling hot water with dissolved metal meets frigid water at bottom of ocean. Comes out of this chimney from deep in the crust, instantly precipitates that metal. That's what you're seeing as smoke. It is the instantly precipitated crystals of that metal. Iron, magnesium, lithium, uranium, gold, silver. Very valuable metal resources at the bottom of these trenches where this is happening. Just covering literally hundreds to thousands of feet thick of these metal deposits down there. You want to stop strip mining our continents, we got to figure out how to scrape that metal off the bottom of the ocean. Here's the problem. It's metal. It's heavy. The amount of energy it would take to bring it up to the surface, currently not economically viable. It's way more expensive than it is to just create another mine.
It's like being used manpower at it. I mean, you could send man submersibles, but that'd be highly dangerous as well.
Well, whether it's manned or unmanned submersibles, it still does not justify the cost.
Yeah.
You can't, the amount of energy it takes to bring up a quantity of metal is not equal to the value of that metal yet. The prices of metals will need to go a lot higher before that's an economically viable solution. Yeah.
And also, even still, there would still be environmental problems either way. So.
Because you could be potentially disturbing habitats at the bottom of the sea. That's true. But there's enough metal down there that we could build a whole fleet of spaceships and just leave the planet. Like legit. With the amount of metal that they estimate is down there, an incredible quantity. We just can't get it. There's actually, there is a movie. Oh, what's it called? Not Abyss. No, where they set up the mining operation at the bottom of the trench. It came out a few years ago. I don't remember.
Which one is this?
That is Hornfels.
The what?
Hornfels.
Oh, right.
That's that baked mudstone, that non-foliated, metamorphosed shale or mudstone. I forget what this movie is called, but basically they set up a mining operation at the bottom of the ocean, and like they encounter these creatures that start killing them off one by one. It's a horror movie, but the whole premise is they're in this mining structure at the bottom of the ocean, so they can't get away, and it's a whole thing.
Oh yeah, I remember the trailer, but
Yeah. Oh, I don't remember what it's called.
I never watched it.
It's got that. I feel like the main character is that female actress from The 100. If any of you ever watched that, I think that's her. You what? You love her? Did you like that show? I loved seasons 1, 2, and 3. Oh, you stopped there? Okay, I think it went for 5 seasons.
Like
6, actually.
6 seasons?
speaking on this subject,
I think I stopped after 5.
like I don't think there's any like large creature like we discovered in deep trenches considering how like significant the treasure is. Only vertebrate that can survive in such deep trenches are like snailfish. So that, and obviously, for example, Megalodon is definitely stationary.
Tons of people ask me if I think megalodons still live at the bottom of the ocean. And yeah, I am an advocate for them being extinct.
It was also a coastal animal. It would make sense for them to live in the bottom of the ocean because they hunted whales.
That's true. Yep, that's true.
Wait, why are you an advocate for them being extinct?
Well, there's no evidence that they still exist. The most recent
3 million?
fossil that we have, I believe, is actually 5 million. I think the most recent megalodon tooth ever found is 5 million years old. There's not really anything alive in the ocean that would support a predator that big.
Because they hunted because it looks in context where there's a bunch of baleen whales that live at the same time of it.
Yeah.
So that's what I wanted.
When you think about how often a great white shark needs to eat, the quantity that it eats, there is nothing of a sufficient number in the oceans now that would be able to support a predator the size of a megalodon.
I believe there's also like zinc. There's a study in nature about zinc isotopes with megalodon, and as the oceans became cooler, their zinc isotopes changed, and they became in direct competition with great white sharks. They also evolved at the same time.
Right. Okay. The bottom of the ocean is very fascinating subject, both for what lives down there, what we don't know lives down there, and other mineral resources down there. Every now and then, bits and pieces of some crazy animal will wash up from a deep sea trench or something. We know that there are giant squid down there. There have been giant squid 20 feet long that have washed up on the coast, right? So I wouldn't suggest going for a free dive. Although, if any of you have watched Megalodon 2, how many of you have seen the Meg 2?
I unfortunately have.
The part where Jason Statham swims without a suit in the trench, and their justification is, well, fish breathe, don't they? Or something like that. Fish don't have a suit.
It's something with pressure and like.
Yeah, he's like, as long as I breathe out all the oxygen in my lungs, I'll be fine.
You'd be crushed instantaneously.
Yeah. Have any of you ever seen an object that went down to the bottom of the ocean and then came back up?
It's crushed.
Yes, it's severely crushed. So I saw several things. A cup of noodles. You know the cup of noodles, like the styrofoam cups? You know how big those are? I saw one that was taken down to the bottom of the Mariana Trench and then returned to the surface. It was about that big.
And though all the submarines come back slightly smaller or like more compressed.
Yes. And if you all know what happened to that submarine on the Titanic, that's not even massively deep. It's deep, but nowhere near as deep as the Mariana Trench. And that thing imploded, reducing a 5-person submarine to about the size of a small sedan. Huh? Yeah, it was not very well made. You take a submersible like that and you put it in the bottom of the Mariana Trench, and then you pop it, it'd be about the size of a basketball. Okay, so the pressures we're talking about, no joke. All right. Which is another consideration why these things have not been mined yet. Okay. Burial. So something remains in place for a very long time, and layer upon layer upon layer, sediment is piled on top of it until you reach that 8-kilometer depth, right? So that you have the high enough pressure and high enough temperature to cause this metamorphism. Okay, that is burial. The same thing is true for subduction. Something gets shoved under another plate until you reach the right heat and pressure thresholds. And then finally, regional metamorphism. Regional metamorphism happens on a much larger scale. Okay, so this is when you've got 2 continents that collide together, and you get this huge, massive area that becomes metamorphosed. Most of the Himalayan mountain range is metamorphosed seabed. Okay, the Alps in Europe, mostly ocean floor, a lot of which has been metamorphosed. I have in my office, when I went to the German Alps back in 2008, 2009, I hiked up in the German Alps and I found a seashell, pulled it out of the rock. It's ocean floor. That is thousands of feet above the ocean surface now in a mountain range. Okay, a lot of which has become metamorphosed thanks to the collision of this happening. Okay, of these 2 continents running into each other. Africa running into Eurasia is what made the Alps, or is a large contributor to it. Okay, there are other tectonic situations that have added to it or started it, but that's where we're at. Okay, so that's what regional metamorphism is. Regional metamorphism, differential stress. Why? You have 2 massive forces. I'm talking about 2 bodies of rock that weigh quadrillions of tons running into each other. Okay. And that's going to create a lot of stress. And that creates a lot of metamorphism. Okay. Then we've got fault zone metamorphism. Remember, a fault is those cracks I was talking to you about in the Earth's crust? Well, because there is motion along those faults, that motion, which we know of as earthquakes, okay, we'll talk about that in our earthquakes lecture. That motion is a result of stress buildup, and that stress buildup creates small quantities of metamorphism. When that happens, we will often end up with a type of metamorphic rock that we call a myelinite. So water kind of seeps down in there, you get that stress buildup, and you get this kind of broken, shattered looking, and then metamorphosed together, kind of fused together. It looks, another name for it is fault breccia, okay, because it's a bunch of shattered pieces that have been fused together. And then here's a fun one, impact metamorphism. What do you suppose I'm talking about with that? When what comes? I love this. I love the sound effect, but what object are we talking about? Meteors, asteroids, comets. Okay. First of all, you guys know the difference between the three?
Well, one's in orbit, right? It's coming into orbit, or like it's saying, like meteor is usually coming in almost in contact to Earth, right? Isn't that correct?
Well, asteroids come into contact with Earth as well at times.
I think it's a size thing. At a mirror, it's an asteroid, it's a size thing, and the comets are just made of different stuff, ices.
Yep. Comet is often made out of just essentially dust and ice, and they're usually in an orbit. And if a comet ever comes close enough to a planet to actually impact it, most of it burns away in atmosphere. Although they can get quite big. There is a comet way out from our solar system, thank goodness, that is about the size of our sun. So that's pretty cool. And then an asteroid, yeah, and a meteorite, it generally comes down to size. Meteorites are usually pretty small. Okay, I think the largest meteorite that's hit Earth in recent times was about the size of a small car.
Wasn't that the Russian thing?
Yep, the one that landed in Siberia. Mm-hmm. Yep. And then you've got the larger asteroids, like the one that killed the dinosaurs.
Is like 11 kilometers, right? The one that
I think the one that killed the dinosaurs was like 5.5 kilometers.
but it's small.
Yeah. But they hit with so much force, it's essentially like setting off 100 nukes all in one spot. Okay. So, yeah.
I would say it's also so powerful that could also literally just roll across when it comes in contact with it.
Yep, there have been impacts on Earth's surface so powerful that it has blasted pieces of the Earth's crust 800 kilometers away. There's actually,
Oh, sorry, if I say, isn't there some that almost reach Mars, right?
some pieces of Earth. Well, that's a debate. That's a thing. We can talk about that tangent in a minute. But there is a crater in Canada called the Sudbury Impact Crater that was such a massive impact that it punched through the Earth's crust and allowed the mantle to come to the surface. As a matter of fact, some of the world's largest mining operations are set up on top of that impact crater because it is the most accessible place where we can reach mantle rock, which is rich in these rare metals. It sent pieces of the Earth's crust 800 kilometers across Canada. We can go and visit pieces of the crust from this impact 800 kilometers away across Canada. It was pretty intense.
I just want to say, you said that there was a comet that was the size of the sun. Talk about the actual like size of the rock that was the comet, or the glowy bit?
The mass of the comet, including its halo and its tail.
Because there was like a comet, which I mean, like the actual nucleus, I guess it's called, was not that big, but the actual coma, I think it's called, was the size of the sun.
Yeah.
Like, is that what they're talking
Yeah,
about?
I'm talking about the whole
Okay,
comet
that's not
itself.
the whole stone of the.
No. And remember, there's not a whole lot of stone generally in a comet.
Because that was Comet Holmes, I think, in 2006.
Yeah. Okay. So the question was brought up just now, whether or not pieces of the Earth that were chucked off from an impact have hit Mars. The answer to that is we believe yes. There are pieces of Earth rock that have gone to Mars because they were ejected off of Earth's surface from an impact. and then they flew around in the solar system until Mars picked them up. Now, this has raised a lot of debate, and this is really kind of leaning into more 1404 stuff, but hey, who doesn't like a good tangent, right? Have any of you ever heard of panspermia? Okay, there are two major groups of thought for how life began on Earth. Number one, life originated on Earth, developed here, the whole amino acids into DNA chains, into bacteria sort of deal. Or panspermia, where life began somewhere else and then came to Earth piggybacking on a piece of debris like an asteroid or a meteorite. And one possible debate is, since we know that Earth rocks can land on Mars because of an impact, maybe Mars rocks have landed on Earth, and we know that's true because we found pieces of them in Antarctica, pieces of rock from Mars. But perhaps life began on Mars and ended up succeeding on Earth because it came here on a meteorite, whereas Mars died fairly rapidly. That is one of the debates that constantly keeps us at each other's throats in the evolutionary biology world. Yeah.
And haven't they also discovered amino acids on space rocks before, right?
We have found organic components on space rock. However, you can make organic molecules without the presence of life. Generally speaking, on Earth, they are due to the presence of life, but we have made them successfully in a lab setting without life needing to be required. And this leads to another interesting question. Does life exist on other places? There are places, moons actually, around Jupiter and Saturn, both of which we know have some form of organic molecules present. There are two places, Europa and Enceladus. Okay, Europa is around Jupiter and Enceladus is around Saturn. Both of them have what we call ice volcanism. This is a fun subject. I actually really love planetary geology. It's really cool. So you know how our planet has a rocky surface and a liquid rock core?
Yeah.
Well, Europa and Enceladus have an ice crust and a liquid water buffer, and then a very hot, we believe, just like a silicate core that is still really warm. Probably because of the push and pull of gravity of Jupiter and Saturn. Okay, so because it's got a hot core, it can keep liquid water on its interior, and therefore you get convection, which causes the ice on the surface to be tectonic. And so you get plates of ice crashing into each other, splitting apart from each other, divergent, convergent, and transform plate boundaries on these moons, just like Earth does, but it's made out of ice instead of rock because the same physics are at play. Now, this means that there are occasionally volcanoes made of ice that shoot water off of off the surface. Because there's very little atmosphere, a lot of this ice kind of flies off into space. Recently, a satellite was flown past the moon of Enceladus, and it picked up samples of this ice, and we believe they contained organic molecules. Now, does that mean there is something living in the liquid water under the ice surface of this moon? We don't know. There could be a whole ecosystem down there for all we know. It fired everyone's imaginations as soon as we found that out. It's incredible. I love thinking about Enceladus.
The problem is that at least in Europa, the ice crust is like kilometers on the
Yeah. Yeah. It would take forever to drill down there to find out. I very much doubt we ever will, but it's fun to think about. Okay. Well, that was a fun couple of tangents. All right. Now, remember that this all happens, metamorphism happens in grades. And so the further you are from the source of metamorphism, the lower the grade of metamorphism will be. So out here on the edges of our mountain range, okay, which is this tectonic plate interaction, we'll end up with slate. That same layer, let's call it shale, that forms slate here at the periphery, down here deeper in the mountain range would form a phyllite. Even deeper down, that same layer would make a schist because it's getting more heavily metamorphosed. And then down here in the core of this mountain range, where the heaviest metamorphism is taking place, the same layer of rock would make a gneiss. And so it will transition the deeper you go into this metamorphic zone because it is experiencing higher degrees of metamorphism. This is just kind of an easy guide chart that shows you based upon the increasing metamorphism rate. Basically, you can think of pressure increasing along with this heat, okay? What minerals you're going to get in different types of rock. For example, slate will often contain chlorite, muscovite, and biotite. Phyllite will often contain all those things, and sometimes garnet. Schist will contain all those things, and garnet and starlite. Gneiss will potentially can contain all those things, in addition to high quantities of quartz, feldspar, starlite, sillimanite, things like that. And then beyond gneiss, you're going to melt your rock because gneiss is the highest degree of foliation. Any higher than that, and you're in the melting zone. Okay. Now, the last thing I want to mention before we move into lab time, we learned that minerals have different melting points. Yes? Everyone's clear on that? What happens? Come on, camera. Stay with me here. What happens if I have a metamorphic rock where I increase the temperature such that only some of the minerals melt? What happens there? Yeah. You wouldn't get holes in the rock, but you're on the right track. Some of the minerals melted.
It would seep into other cracks, creating almost like striations, I assume.
You wouldn't make striations, no. Let's say I have a folded gneiss. It's got amphibole, it's got quartz, it's got feldspar. In those banded, foliated layers that we see gneiss have. I melt, or I don't melt, but I increase the temperature, the quartz melts. I increase it even more. The feldspar melts. And then I stop there. I don't quite reach the melting point of amphibole. And then I lower the temperature again. What's going to form as I lower the temperature? Solid what? What did I melt? Quartz and feldspar. So what am I going to make when I lower the temperature? It's the obvious answer. Quartz and feldspar. That's what I have the ingredients for, right? However, I melted metamorphically changed quartz and feldspar, and I am reforming igneous quartz and feldspar, and that gives me a migmatite. Notice how I still have my foliated bands here. I've got folded rock. These layers are still folded. The difference is my amphibole, which never melted, has retained that folded structure, while the quartz and feldspar did melt, became magma, recrystallized, and now I get large unfoliated quartz and feldspar grains. This is essentially a metamorphic and igneous rock. It's really weird. This is really the only time that can happen. I have my folded structure and the amphiboles are still foliated, but my quartz and feldspar have recrystallized and made igneous crystals. Isn't that crazy? I'm going to pass this around.
Is it turned into granite?
No, I mean, basically these layers of quartz and feldspar, that would be granite, but it's inside a metamorphic structure.
That's something like strands of granite in the...
It's basically like having veins of granite in there, I guess you could say. Yeah. Pretty crazy. All right, well, that's what I've got for our lecture today. Lab 4. Oh, it zoomed in on me. Let's zoom out. There we go. Lab 4 is over metamorphic rocks. And just like usual, the Lab 4 PowerPoint is literally just a recap of the things I taught you how to do in class. What do we got here? We've got different foliations. We've got non-foliated textures. We've got what metamorphism does, kind of a breakdown of your process. And these are the questions you're literally just going to answer during the exam, not during the exam, during the lab. Okay. So it's pretty straightforward. You're all used to the drill at this point. All of my labs are the same. This is the last sample identification lab you get, by the way. Lab 5, nothing to do with samples. That's about maps. Okay. Huh? Topographic maps in particular. Yes. All right. Any questions for me before I end this recording? No? Please remember, my online students, send me your questions for the exam review no later than Wednesday night. Yes.
How would you review Meg 2 as a movie?
Let's talk about that after I end this.